everyone. Thank you so much for joining us for the first ever Insights Exchange brought to you by the Ideas 42 Academy. We're very happy to have you here to get a behind-the-scenes look at one of our exciting new initiatives, behavioral science and machine learning. So I'm going to hand it off to my colleague Rachel, and we'll get started.
Excellent. And so let's try to get those slides up. So good morning, everyone. My name is Rachel Rosenberg. I'm a senior associate here at Ideas 42, and my background is in econometrics and development economics, as well as behavioral science, and I lead the machine learning portfolio here at Ideas 42. So let's get some slides going. And so as we get that started, I'll just encourage you throughout the presentation here to add questions to the chat room on Zoom, and then we'll take about 10 minutes towards the end of the session to field those questions. Great. Looks like we're going. So this is a presentation on behavioral science and machine learning. And the idea is to give you a primer about how we're combining those two fields to add social impact. And in addition to that, we'll talk a little bit about ethical perspectives and applications of machine learning, especially as it relates to social problems. But before we do that, I want to do a quick introduction to behavioral science. So behavioral science asks the fundamental question, who are we really? And as program designers, as policy designers, sometimes we take different views of humanity. So sometimes we take a view of humanity that resembles this character. So some of you may have seen this before. This is Spock. And what's unique to Spock is he is a traditional econ. He weighs his costs and benefits. If the benefits outweighs the cost, then he's going to choose that decision. If not, he'll let it go without even looking back. What we know is that humans don't actually behave that way. We're not quite as linear in our thinking. And so sometimes we'll take a different view of humanity and we'll design programs and policies for a character like this guy. So this is Homer, and his character is distinct from Spock in that he is entirely impulsive. So if you put a big plate of hamburgers in front of Homer, he has no self-control and he will gobble them up. And he just acts as his emotions tell him to act in the moment. So we know that humans are neither Spock nor Homer, right? We are actually more like these people. So this is kind of funny. These are individuals who have made the right decision. They're getting healthy and going to the gym, but they can't take the stairs on the way in, but instead have chosen to take the escalator. So they'll burn 1,000 calories on the elliptical, but can't burn 5 on the way in. Why is that? Well, it's because the environment is influencing them to take the escalator because it's simply there. And so behavioral science helps us understand how context and environments and the cues in those environments affect humans' behavior. So if we think about what the traditional economic behavioral model looks like, it's deterministic and it's linear. So the idea is that decisions are followed by actions, and then we get the outcome that we intend to get. So we assume that if the benefits outweigh costs, then we'll decide to pursue a decision, and that's a natural process. So let's think about that with a real life example. So I, for one, try to cook every night of the week during the weeknights. So that's 5 nights a week. And my intentions are strong. I want to be healthy. It helps save me money. But sometimes I don't feel like cooking, or maybe I want to go out with friends and I've had a long day at work, and so I don't, get home to cook. Or maybe on the weekend before I'm preparing for the week, I'm stressed out, or I'm having fun with friends and I don't end up going shopping and buying the ingredients I need. And so really the behavioral model looks a little bit more like this. Now this can look like a mess, but really what's important to take away here is that there are contextual cues that affect individuals' behavior. And behavioral science is the study of how those cues actually do that and the psychological relationships that we have to our environments and how that affects our behavior. And so while this looks messy, there are actually lots of trends that we've studied carefully that help us predict how people act, and then help design environments that will help people do more of what they want to do and less of what they don't want to do. And so that's what Ideas 42 does. We use insights from behavioral science to work with nonprofits and governments, and when it's mission aligned, other companies, to solve some of the world's most persistent social problems. So that's quick, but that's the intro to behavioral science. And with that, we will get into Machine Learning 101. So what is machine learning? Well, the first thing to know is that machine learning solves prediction problems. So if you have an econometrics background, or if you work for a nonprofit and you think about different types of problems, often the questions we ask are causal inference problems, and those rely on estimation. So on school attendance Y. So we want to know, what is the relationship between X and Y? And that's something that we use BHAT to predict. Now, if it's a prediction problem, it looks a little bit different. We want to predict the outcome. So we would ask which students will attend and finish school. Let's take another example that's a little bit more behavioral science oriented. So we might ask, what effect will a social norms intervention have on savings rates? And that's a causal inference question. But the prediction version of that question is, for example, which employees are more likely to save for retirement? So let's use a more concrete example to make that a little bit more fun. So what about the example of categorizing photographs of cats and of dogs? Now, this is a pretty easy task for humans, but until recently, this was actually a really difficult task for computers. So how do you train a machine to learn how to categorize photographs of cats and dogs? Well, what you do is you create a predictor by feeding a computer labeled photographs of cats and dogs. And at first, it won't be very good at this prediction, but then you feed it more and more and more and more images of cats and dogs, and slowly it gets better at understanding the different features of those photographs that make it a cat or a dog. The important part though, so if this was the model that we were using to do that, we would feed these correctly labeled photographs of cats and dogs as our training data to a machine learning algorithm that creates the predictor. And then we're going to ask that machine to categorize a new photograph that is unlabeled, that it's never seen before. So let's pretend we're feeding it this picture of the cat. So that's going to be the new unseen photograph. We feed that to predictor, and then it's going to give us a prediction, whether it's a cat or a dog. And in this case, we would hope that it predicts cat. And what's important here is that machine learning has to work out of sample. So it's not as important to make sure that the machine can predict what you have in your training data, but rather new data that's unseen and uncategorized. So in other words, the predictions have to work well out of sample. And to demonstrate this point, imagine that my training data was made up of cats that looked like this. So 75% of the cats in my training data are brown. And then I fed my predictor this picture of a dog. Well, what might happen is your predictor might anticipate that this is, and predict that this is a cat, right? And so the point here is that this is a problem that we think a lot about in machine learning, which is trying to figure out how to balance that trade-off between predicting things that are in sample in the training data set and things that are out of sample, that are in new unseen photographs. Okay, so hopefully now that gives you a sense of how machine learning generally works. But what about problems that we actually care about? You know, we may not care so much about categorizing cute pictures of cats and dogs, but what about other problems? Well, in 2005, Sendhil Mullainathan, our co-founder for Ideas 42, and some other advisors and affiliates, John Kleinberg, Jens Ludwig, and Ziad Obermeyer, wrote a paper on what they call prediction policy problems. A prediction policy problem is, what they argue, a problem where causal inference is going to be less important, and actually predictive inference is going to be able to solve social problems. So what are some examples of that? Well, in the paper that they wrote, they thought about significant joint replacement surgery. So that might be a knee replacement surgery or a hip replacement surgery, where you wouldn't really get very much out of that surgery if you're in your last year of life, right? And so understanding, well, could we predict how long a patient will live after that surgery? And that will give us a sense for whether or not there's a benefit of conducting that surgery, saving costs for those for whom it doesn't really make sense, and we may be redistributing those for individuals who really could benefit from the surgery. Other examples might be thinking about high-risk youth who could be targeted for an intervention, even predicting what teachers are going to be most effective in which classrooms. And one that we're particularly familiar with at Ideas 42 is the question of release for bail. So when judges are given a list of individuals who have been arrested, they have to make a prediction. And that prediction is about whether or not that individual will first return to their court date, and then in some states, depending where you are, also whether or not they're likely to reoffend and whether or not they're going to be a threat to society or to others if they're released on bail. So that's a fundamental prediction problem. And what we've seen both in our work with Jens Ludwig at the University of Chicago and also in simulation studies is that an algorithm will do a lot better job at reducing the bias and predicting reoffense. That said, there's a really important role for behavioral science in the adoption of that algorithm. So it's one thing to say, hey, we can improve upon judicial decision-making by giving you a recommendation. It's another thing for the judges to actually take a look at that recommendation, use it in their decision-making, and have that achieve the intended outcomes from implementing that tool. And so that's the way that we start to think about how behavioral scientists can have a really important role in the implementation and the adoption of prediction tools. Now, that's really just the tip of the iceberg in terms of the opportunities to combine machine learning and behavioral science. So what I just presented is types of problems that are supervised machine learning problems, meaning that we already have the labeled photographs of the cats and the dogs. We already know how to categorize the information that we have. There's a whole field that uses unsupervised learning, where you don't even have to have pre-labeled versions of the data. There's also other opportunities to apply prediction to causal inference. And so I know I told you before that prediction and causal inference is the difference between what we traditionally think about and what machine learning thinks about. Turns out machine learning has a lot to offer for the causal inference world, and that's actually become a big part of our portfolio here at Ideas 42, and I'll get into that a little bit in this presentation. But before I do that, I just want to mention that we recognize that algorithms have been used for the dark side. And we believe that there is a new generation of computer scientists that are contending with their past and looking for opportunities to adapt algorithms for good. And that's where we're focused. Great. So like I mentioned before, please put your questions in the chat room. For those of you who might have joined late, we'll be taking questions at the end of the presentation. So how can we then combine behavioral science and machine learning? So today what I'm going to share with you is about a couple of years ago, we started a portfolio where we conjectured that by combining behavioral science and machine learning, we could have more social impact. And I'm going to share with you now how we believe behavioral scientists and individuals working in the nonprofit sector, individuals working for social good, are positioned to use machine learning. So I'll do that by sharing our approach to machine learning here at Ideas 42, talk a little bit about what we've accomplished so far, explain how we're challenging ourselves to think about ethics, and lastly, what's next for us in terms of machine learning and behavioral science. So let's get into it. Our portfolio is comprised of 3 approaches to combining behavioral science and machine learning for social impact. And those 3 categories are augmenting decision-making, so that's that field of prediction policy problems, re-engineering design, which has to do with what we know about machine learning for how we can design and understand experiments better. And I'll explain each of these in a little bit more detail in a minute. And finally, expanding our understanding. So using different algorithms that help us understand trends in big data, that help us get underneath some of the assumptions that we enter projects with inadvertently. So you can think about that first category as being behavioral design applied to machine learning, and those second 2 categories as machine learning applied to behavioral design. Great. And our approach here is to partner with leading academics, recognizing that this is all very cutting-edge technology, and there's this new field of computational social science that is working to combine social science and computational methods. And so here are 5 of our very involved advisors in this effort. That includes Professor Susan Athey and Jan Spice at Stanford University, Sendel Molnathan and Jens Ludwig at University of Chicago, and Professor Ziad Obermeyer at UC Berkeley. So let's talk about this first category, which is augment decision-making. So this is the prediction policy problem category. And the goal here is to improve the design of predictions and the tools in which those predictions are embedded to improve people's lives. So as behavioral scientists, we have a particular approach to problems. We understand that if you just build something, people won't necessarily come. And it's not because they don't have information about it existing. There are other things that are at play. So once we've defined a problem, let's say with the pretrial release assessment that there are more individuals being held and not released on bail than could be released who are safe to society, then we would go through the process of diagnosing, well, what are the behavioral levers and what is the psychological relationship that a judge has to that decision in those moments that might influence them to make less than optimal decisions. Then we would think about how those levers could relate to design methods and how an algorithm might be able to be designed and the information could be presented to those judges in a way that would either, let's say, reduce their workload, change their relationship to that decision, or even blind them from some of the biases that, while they are supposed to not have, we as human beings always have. And so the idea here is that if we can design algorithmic tools that improve how people use those algorithms and increase the adoption while also allowing the human being to have their opinion for those fringe cases that might be concerned about, because of course not every algorithm is going to be 100% perfect, then they can achieve that intended impact in a way that they wouldn't otherwise achieve. So what methods go into that category of work? Well, we rely very heavily on the academics that we work with to decide what types of models to use depending on the context. And of course, it's going to depend on what data are available and the nature of the problem. But here are some examples of methods. So there'll be regression methods, which are linear, which many of you might be already using, but that also includes ridge lasso, polynomial. There are also a set of classification algorithms like decision trees, k-nearest neighbors. We also implement some with neural nets, and then ensemble methods improve upon all of those methods to make the predictions more accurate. So what are some examples of this in our real work? Well, we already spoke about in the safety and justice portfolio how we think about release assessment among judges. And in that case, our teams have worked with judges to think about how we could present information to them based on the algorithmic decision about whether or not to release someone on bail. But ultimately, it's up to them to make the decision about whether or not to use that recommendation. In the health portfolio, we have a project where we're thinking about a heart attack risk tool. So when individuals come into the emergency room with advanced coronary syndrome, which is termed ACS, basically people come in thinking that they're having a heart attack. There's an important prediction task, which is, should this person have a cardiac stress test? And a cardiac stress test, not unlike the joint replacement surgery, is actually a stressful and expensive operation to go through. And some people are actually negatively affected by going through that stress test. So by predicting what the outcome of that test will be, doctors can improve upon their decisions in the emergency department. Now, what's interesting is that just because you give a physician a decision support tool doesn't mean she'll use it, right? And so trying to understand, well, what is a physician's workflow when she's in the emergency department? How does she get information? How does she weigh the costs and benefits of different decisions? And what goes into that relationship between her and her prediction? So that's the heart attack risk tool, and we're doing that right now. Another field that we're working on this in is the economic justice field with a reemployment placement program. So again, when a worker is re-entering the workforce, they have to make a prediction about what program is going to give them the most benefit when they're trying to retrain. And so we're working right now on training an algorithm that uses data on previous employment programs to try to understand what workers will benefit from which program. So it's a little bit more like a matching problem. And lastly, in the health area, we have two projects that work with opioid use disorder. So one is a risk assessment, understanding. So Justine Hastings is working on an algorithm where we use government records to train an algorithm to understand whether someone will be at risk for opioid use disorder upon their first prescription. And similarly, there's a program that works to place individuals that have already experienced opioid use disorder in advanced programming. Again, in both of those cases, you have a prediction problem. So if you can predict individuals who are going to be at risk, maybe you try to give the doctor a recommendation about whether she should prescribe that opioid in the first place, or maybe there are opportunities for certain patients that are going to get a lot of benefit out of that being referred to certain programming. And so again, it's one thing to have the algorithm, it's another thing to think about how to build that and design that into the decision action framework that exists for individuals on the job. Great. So let's go into the second category. And this is going to be in the machine learning methods applied to behavioral design area. And we call this re-engineering design. So this requires a little bit of background information about how we run projects here at Ideas 42. So whenever we can, we try to test. And we try to test with what we call a randomized control trial, which is the most rigorous way of testing whether an intervention works. And you do that by having a control group, and you test the outcomes of a control group against what we would call a treatment group, or individuals that receive an intervention. So what's really important is that when we run a randomized control trial, we pick up on something that we call an average treatment effect. And that's, on average, how well did something work. Now, we might have some hypotheses ahead of that test about what subgroups might experience that treatment differently. So let's say that we're running an intervention in a community college. We might expect that individuals that are first generation would experience a financial aid intervention, or emails and texts about whether or not to file financial aid, differently than individuals whose parents did attend college. So those would be what we would call a priori hypotheses, and we would be able to look at those in basic regression analysis. What machine learning methods add to that evaluation is it allows us to, without specifying a priori hypotheses, explore the relationship between all the different characteristics in the data set and individuals' response to treatment. Now, it's interesting to learn about that, but the purpose of doing that is not just this exploration, but instead to come up with a personalized treatment policy for every individual that could be assigned to the treatment. And so what that results to is ensuring positive impact for those who receiving different versions of the treatment is most effective. And then there's, of course, going to be a group of people for whom the treatment isn't working. And so there, the onus goes back to the researchers to figure out, well, why is that population not responding? And how could we do more in-depth qualitative research to design another intervention that could get at that population's needs? So the methods that we use here, again, rely very much on our research teams at Stanford University and otherwise, but we use regression trees and random forests. Those are often tested against X-learners and neural nets. And then we've also advanced a little bit into using contextual bandits and general adversarial networks. Now, there's not time in this presentation to go into each of these different methods, but feel free to ask questions or follow up with us later about how each of these methods plays out in this endeavor. Great. So what are some examples of projects for which we're doing this? Well, sorry. So before I get into that, when selecting a project for personalization, there are some important criteria to consider. And this is a little different from a prediction policy problem because really the data have to be right for this type of exercise. And so we've identified that there are, I think it's 7 criteria for personalization. So the first is that personalizing the intervention would add social value in the first place. So there's real reason to personalize the intervention. And the second is that it's a well-powered sample. So this is true of all data science, which is that you need to have large data. But also in this case, we're looking for significant average treatment effects out of a randomized control trial. The data also need to be wide because all of those covariates are going to influence whether or not you see interesting subgroup effects with the intervention. There needs to be diversity in the sample population, which means that when you're thinking about the different people and how they'd respond to treatment, if the group that you're intervening on is super similar, then you might expect everybody to respond basically the same way. But if you have a really diverse sample population, then it's more likely that you'll see a diversified effect or diversified result from treatment. There's also an important piece here, which is that you want to be able to vary treatment arms because if you can vary the delivery channel or if you can change the framing on the intervention, maybe change if it's done in person or through a Skype call, that might solicit different responses from individuals that experience that treatment. And finally, thinking about scope for follow-up, because just understanding that there are differentiated effects across different individuals doesn't really get us to social impact, and that's our goal here. So the idea is that if at scale you can follow on and experiment with that personalized policy, then we can really see what is the above and beyond social impact of implementing machine learning for personalization. Okay, so now to the examples. Some of the places that we've been implementing this type of exercise is in financial health by understanding retirement contributions with an intervention where we showed individuals an aged selfie, so a selfie of themselves at retirement age, and then encourage them to increase their savings for retirement. Another is increasing financial aid refiling for students in community colleges. A third is in the civic engagement portfolio, so that's increasing voter turnout among non or unlikely voters in elections. And finally, in the economic justice portfolio, helping drivers avoid catastrophic debt that's associated with lots of tickets and potential booting. And so in each of these cases, we've seen a different range of heterogeneity based on the characteristics of the population, the way that the treatment was designed. So that said, we've learned a lot about what it means to design explicitly for this personalization. So when we run a randomized trial, often we power it so that we can see an average treatment effect. And we think about choosing just as many treatment arms as make sense for the partner, and we think about costs. And what we've learned is that can be limiting in terms of how much we learn about heterogeneity in the treatment effect. And so if we really want to design for personalization, there are a few things that need to happen in the pre-analysis planning for experiments that allow us to do this better. So the first thing is to power pilots to detect heterogeneity, which means bigger samples. This isn't always possible, so sometimes that also means just simulating diversity in the population and trying to get as diverse of individuals in the sample as possible. It also requires varying treatment arms, because if you want personalized policies, you need to have a variation of things tested. And also, in all of these cases, it's important to have strong data infrastructure. So a lot of organizations are still developing their data infrastructure, and that's great. And someday they'll be positioned to do these exercises as well. But there are also lots of sectors that serve social good that do have strong data infrastructure, and those are the places to really start implementing these types of exercises with data. Great. So our third and final method in our portfolio has to do with expanding understanding. So as behavioral scientists, when we approach a problem, we go through an extensive process of defining the problem and diagnosing the behavior. And what we mean by that is just because somebody comes to you saying, people aren't coming to our training program, or people aren't saving for their child's future college education, doesn't necessarily mean they don't know about it. It doesn't necessarily mean that they don't want to. And maybe that's not always the problem. Also, often we'll say, oh, well, we're interested in the whole city of San Francisco or the whole city of New York City, places that have millions of residents and really different people. And so in those settings, there's a lot of data to look at to understand those problems better. And so the idea here is to use advanced technologies and machine learning to improve how we look at data sets, to unveil trends and help us better define problems and better diagnose behavior. And what this really does is helps us get underneath the assumptions that we bring to the table as researchers, and really just look at what the data have to say. And so in doing that, there are lots of methods we can use, but the difference between expanding understanding and the other pieces of the portfolio is that here we're using more unsupervised models. And so that means unsupervised clustering methods like k-means clustering or agglomerative hierarchical clustering models, which basically don't require labeled data and allow us to explore relationships between individuals in a population without having a priori hypotheses about what matters. So a couple of projects that we've worked on with these methods include a project to understand financial behavior to improve savings and resilience among individuals who are employed, and another project where we were understanding the uptake and use of college savings accounts, like I referenced before, in a large city in the United States. Both of these cases, we either confirmed or disconfirmed what we understood about those environments, and it helped us move forward with a better definition of the problem and also a better understanding of the behaviors at play. Great. So again, if you have questions about that section, feel free to add them to the chat, and we'll answer them at the end. This next piece is about ethics in machine learning. So just like any tool, machine learning can be used for harmful intentions. And we are there are important organizations that are thinking about those algorithms. For us, that's less important. What we're more concerned about is algorithms that are intended for social impact, but might unwittingly perpetuate bias. And so that's why we've built out what we consider a fairly robust but work in progress framework for addressing those, for thinking about what those problems are, and then presenting strategies for our team members to think about those difficulties. So to get started, let's just think about, well, what are those risks? Well, algorithms that perpetuate bias are making headlines across sectors. So you might be familiar with BERT, which is Google's technology, natural language technology, that has been accused, rightly so, of perpetuating bias by identifying computer programming with maleness. And one result of this is that women at one point were less likely to be shown ads for high-paid jobs on Google compared to men. There's also facial recognition technology that's being used in policing, which has also been accused correctly of more falsely matching and identifying Black faces than white faces. So what's going on with these different types of risks? Well, the first problem is bias in, bias out. So before, when we learned about how machine learning works, we saw that it requires training data. And if that training data is already biased in the first place, like let's say individuals who are interviewing for computer programming jobs were more likely to hire men, or men were more likely to self-select into computer programming fields, then the machine is going to learn that same trend and perpetuate the bias in decision-making around maleness and computer programming. The other problem that's represented here is this idea of representation in the data. So if facial recognition technology is entirely trained with a majority of white faces, then it's going to be a lot better at matching white faces and a lot less good at matching Black faces. So that's one of the first sets of risks. But just the data isn't the only risk here. So there are important programming decisions that go into designing an algorithm. So there's an algorithm that was designed for a health program to address individuals with chronic conditions. So let me show you a graph here. So this algorithm basically was making a decision for individuals who had advanced chronic conditions in their health, whether or not they should be referred to a program. And first they get screened, and then there's a default into that program. And that program for insured individuals comes at no cost to them. And everybody in this study is insured. So when you look at this chart, what you'll see is that the y-axis is the prevalence of chronic conditions, and the x-axis is the percentile of the algorithm's risk score. Now there are two lines here. There's a purple line and a yellow line. The purple line represents individuals who are Black, and the yellow line represents individuals who are white. So what do you notice here? Well, there's a clear gap in the number of chronic conditions among Black individuals and white individuals at that point of default and screening referral to this important program. So why might that be? Well, some of you might be familiar with this study by Dr. Obermeyer and Sendel, Mullainathan, but basically the algorithm was using expenditures on health as the outcome. And in doing so, it was using that as a proxy for health. And anybody who works in the health sector knows that health is a very multidimensional outcome to measure. And just using expenditures is going to fall short in terms of measuring how people are in terms of their health. And it turns out that it also perpetuates bias, because by using expenditures instead of a more multidimensional version of health, and because Black individuals who are insured happen to spend less money in the health system than white individuals on care, you see this discrepancy between who gets referred to the program and not. And so the finding here is that this algorithm exacerbates discrepancies between Black and white insured patients. So what was the issue here? Well, in one case, you could use expenditures as your outcome of interest when creating a prediction model, or you could use a more multidimensional measure of health that would have gotten you much closer to an accurate referral to an important program. An important point that Sendel makes in relationship to this study is this idea that an algorithm is actually a lot easier to fix than a biased person. So at least with an algorithm, so with both an algorithm and with a person, we can observe biased outcomes, right? But that's kind of where the similarities end. So at least with an algorithm, we can understand the way that the algorithm designers programmed it and back into what's the stem of the bias. Whereas it's very hard to talk to an individual and actually get back to the real reason why they might have made a biased decision because of all sorts of things that we know about human memory and perspective. The last and also very important thing and risk when considering ethics is that a fair outcome is a fundamentally subjective notion. So these images come from a study from ProPublica where they looked at an algorithm that Compass was using as a pretrial release assessment. So you'll be familiar with this because we've talked about release assessments before, but again, a judge is making a determination of someone's risk for, in this case, reoffense. So if you look at these photographs, you can see the risk scores across white individuals and Black individuals. So here you see there's the scores, and you can see that those offenses, those previous offenses don't exactly line up with those scores. I'll show you another one here where the images on the right. So you see a lower risk score for the white individual and a higher risk score for the Black individual. And you can see that their priors are much different, and the white individual's priors are much more advanced than the Black individuals. When you look at the distribution of the algorithm's scores for different defendants, you can see that the Black defendant scores are much more equally distributed, whereas the white defendant scores are skewed to the right, meaning that more of them are categorized as lower risk. And so when ProPublica took a look at Compass's algorithm, they said, well, this is not fair because individuals are more likely to be falsely predicted to reoffend if they're Black than if they're white. The algorithm designers came back and they said, well, actually, no, it is fair because in each decile of the algorithm's decisions, the same number of Black individuals and the same percentage of Black individuals and the same percentage of white individuals reoffend. So the outcome is equal between the two. While we might agree with ProPublica's assessment of fairness, the truth is that they're both right because they're both defining fairness, but in a different way. And so we have to ask ourselves, with a community of people who are going to be influenced by these types of decisions, what does it mean for an algorithm to be fair and align on those principles? So let's get into a little bit more of how we mitigate some of these issues. So we talked about biased data and representation in data. We talked about that programming decisions matter a lot. And we talked about fairness being a fundamentally subjective issue. None of these issues and risks have straightforward solutions, and that's okay. So this is a work in progress, and this is something that as social scientists and as researchers and individuals who understand human rights, we need to be thinking about how to address these risks. And so our framework here, for that reason, is based on 3 core values. So the first is participation. Participation because we know that fair is subjective, and even defining the problems that we should be addressing is something that's not just an issue for algorithm designers, but also for communities. And so we want to engage with key stakeholders and key community groups to understand what does it mean to be fair, who are the groups that we consider to be vulnerable, and even what are the problems that we think we should be addressing with this type of technology. The second is rigor. So we know that the advancements in machine learning and the technology of programming algorithms are constantly changing. And so we have to stay up to date on how researchers are making different types of programming decisions and how that affects the way that issues change. So staying up to date on the most current research. Lastly, transparency. This doesn't necessarily mean being able to open up that black box and see inside the algorithm, but instead it's about understanding how we define fair, being explicit about the decisions that we make when programming algorithms, sharing that with the community and getting real active feedback and having open discussions about what that means. So our framework for addressing ethical considerations walks through 4 different steps. So it outlines the risks, presents a principle, gives guiding questions and resources, and then provides opportunities to engage with stakeholders. And we're doing this at every stage of our project. So from the beginning of a project when we're selecting a project and a partner, all the way through data collection, applying the machine learning algorithm, and then deliberately evaluating the fielded policy and program to see if it's having the impact that we anticipate. So what's an example of this? Well, let's look at data selection, since we've talked more in depth about those risks. So what did we say the pitfalls were? Well, data could not be available for all groups, and that missingness could perpetuate bias. Data could not be collected correctly or equally for all people, again, with the opportunity to perpetuate bias. Data could be labeled with a biased system, and potentially consent could have not been established with the population for whom the algorithm will function. So the principle here is make sure data are as complete and representative of the full population as possible. And with that come some questions. So team members have to ask themselves, what are the data sets? What are the outcomes available? And to what extent could these introduce or measure or perpetuate bias? Who's missing from the available data set? And is there a chance that that missingness will perpetuate underrepresentation? And are there opportunities to add more inclusive data, even if it comes at a cost? And then also, what consent procedures exist? Then the idea is to gather feedback from the community about those questions, share the questions about missingness with stakeholders, really align on what it means to be in a vulnerable subgroup, and finally, establish consent procedures and a fair data use policy around the algorithm and the systems that it might integrate. So I wish that I could take you through our whole framework today, but I can't. So I wanted to present you the 5 principles that this exercise presents for individuals working with both data science and issues of social impact. So the first is select appropriate problems and values-aligned partners, people who are willing to work with the community, are open to these ideas of transparency and fairness. Make sure the data are as complete and representative of the full population as possible. Involve key stakeholders in the development of the model and its accuracy criteria. Implement fairness packages that reflect a shared definition of fairness, something that's been agreed upon with the community. And finally, routinely test and evaluate this algorithm as it's fielded to make sure that it has the intended impact, and also to understand whether it's perpetuating any bias. Okay, with that, talk a little bit about what's next, and then we'll open it up for questions. So you'll recognize this slide. Our portfolio is comprised of 3 approaches to applying behavioral science and machine learning together. Part of that is applying behavioral design to machine learning through augment decision making. The other side of that is using tools from machine learning to improve the way that we do behavioral design. And across those, we have some strategic positions for how we'll move forward. So around augment decision making, we'll continue to apply behavioral design to prediction problems because we know that that's going to positively impact decision making where there's opportunity for predictive inference. The second is to design for heterogeneity, to add social value to our projects and improve upon how we can personalize interventions, especially in data-rich contexts. Sorry if we have a little background noise there. And lastly, we'll expand our understanding of behavior by using advanced machine learning methods that will help us define problems, diagnose behavior, and improve the way that we understand the world that we're working in. So with that, I will open it up to questions.
Great, and we do have a question in the chat field, which is, what kind of research should you conduct to determine whether and the extent to which your intended audiences will accept and or will act on a recommendation from a prediction tool?
Really interesting. Yeah, so to what extent? I think to a very large extent is the answer, but I'll talk a little bit more in depth about how we would approach that. So the first thing that we would do when scoping a problem like this is to go look at the decision action environment in which usually professionals, experts are making those decisions. What's interesting is that every day we use algorithms, right? So when I am on my way to work, I take a look at my Google Maps to see if my train is not working, if there might be a more optimal route for me to get to work, right? All the time we're using automated suggestions to improve our lives. Where that changes is when there's an expert that has to make a prediction, where they have lots of experience having made the prediction before, and they're not so inclined to adopt something that they think maybe doesn't know as much as them. And there's a range of individuals that experience this, and people change and depending on the context they're in. So what do? Well, you go into those environments where those decisions are being made, talk to the experts about how they're weighing the different decisions that they make, and try to understand how an algorithm wouldn't just improve upon their decisions, but maybe make their lives easier, improve their workflow, change their relationship to risk, that kind of a thing. So it's a great question. I think the most important thing to remember is that qualitative research and problem scoping and selection is really an important first step when entering this field.
Great. Well, the questions are starting to roll in now.
Okay.
Next one is, why would a human need to be involved in prediction policy problems if the algorithm is better? And follow-up question, what does that mean for the role of a behavioral scientist?
Really interesting. Okay. So you might argue, well, if the computer's better at it, just automate it, get rid of the human altogether. What we know about a lot of algorithms is that they're not 100% accurate. And so there are going to be fringe cases in which case an expert is going to be better than the machine at making a decision. And so one strategy for this is to figure out how to filter those fringe cases in a way that allows experts to spend most of their energy working on problems that are more difficult and less of their energy on the more predictable outcomes. So that's one reason. Another is accountability, right? So at this point, an algorithm designer doesn't have responsibility for the outcomes of what happens, let's say, in the emergency room. But the physician does. And so unless the physician is there to vouch for their decision, then she might get in trouble if she's just leaving herself out of that decision altogether. So those are a couple of reasons to consider adding a person. In terms of the role of behavioral scientists, I mean, I think that we know that there's this complex psychological relationship to an expert making a decision. And so we want to do our best job at integrating and designing for their workflow so that there's a smooth adoption of these types of recommendations and that they, like we say, achieve their intended impact.
Great. Got a third question. From the work, what have been some of the most surprising behavioral barriers identified with integrating machine learning into understanding the context that you likely wouldn't have identified without machine learning methods?
Interesting. Okay, so there are two questions there. One is the relationship, the psychological relationship to the algorithm. The other, is things that we discovered that we wouldn't with the algorithm itself. So those are two sort of different questions. So with the first question, one really interesting finding with our work with judges is that while technically judges are just supposed to think about whether or not someone will reappear in court, there are other really important things that judges do consider when deciding whether or not to let someone out on bail. And so, for example, the algorithm wasn't considering someone's home address in the decision about bail. Turns out if somebody lives with a domestic partner and the case is about domestic abuse, you might not want necessarily to release that person back to their home where the individual who might have been victimized in that setting would experience that person before their decision is adjudicated. So that's a situation in which we learned a lot about what goes into the process of how a judge makes that decision, which then in turn can be built back into the algorithm. And so that's really, this idea of participation in the design of the algorithm itself is important because if the judge has some say into what's important in that decision, then they're going to be much more likely to uptake and use that algorithm. So that's on the interesting findings around why people do or don't make decisions. In terms of unveiling trends, so using machine learning to look at data that we, as human beings, just don't have the capacity to take in all the information that's there. One thing that we looked at was the way that individuals in a large city, which there are a few large cities, so choose your pick here, but in a large city, we're saving for their child's college future. So there's these 529 accounts that allow you to save for college tuition. And what we saw in this large data set is that there were groups within the city that were sort of geolocated in the same places, but were very different in terms of race and ethnicity, which were, the program designers thought huge drivers here were race, ethnicity, language in terms of uptake of the program, but you actually saw density of location having a really important influence over that. So what did that do? Well, it allowed us to go into those neighborhoods and learn more, basically.
Great. So, serving as a last call for any other questions. If you've got a burning question that hasn't been answered by this presentation, please get it into the chat window in the next few seconds. Otherwise, we'll be able to wrap it up.
Great. Yeah. Well, thank you everyone for tuning in today. This has been really great. And we appreciate your questions. And like Mitra said, please feel free to reach out to us with more questions. I believe that we'll be circulating a list of citations for the presentation, as well as some recommendations for further reading if this is something that is exciting and you want to get more into.
Great. And nothing else has come in, so we can go ahead and wrap it up. So echoing Rachel, thank you very much for joining us today. And, thank you, Rachel, for providing our first ever Insights Exchange presentation. I hope that you all found this very useful. And to that end, we would love to hear from you. So look out in the near future for a survey coming to your inbox. We'd love to get some feedback from you on this. This is a new offering that Ideas 42 is presenting as part of our new Academy feature. And to that end, we have a couple of exciting opportunities to engage with the Ideas 42 Academy coming up. On February 10th, we have our first ever crash course, which is a foundational one-day look at the fundamental principles that practitioners can use to understand behavioral science and apply it in their own work. And the next Insights Exchange installment will be February 20th, and it will be a look at some of our work in Peru with behavioral intervention to increase hand washing. You can find out more information about both of those and all of our other Academy offerings at ideas42.org/academy. And thank you again for your time and for joining us, and we hope to see you soon at another Ideas 42 Academy installment.